Today is going to examine the electrolysis of water. This is from Ward Science. And the procedure, Liza, the procedure, Colin, is associated with running electricity through water to break the hydrogen and oxygen bonds. So you're basically going to be making hydrogen gas and oxygen gas. And you're going to have this in a petri dish. You'll see it over there. And the hydrogen is going to be detected by a universal indicator. Like a pH scale. Yeah. So what part of the pH do you think the water will produce that's acidic?
Oh, isn't it, I forget, is it lower or higher that's more acidic?
7's the base.
Okay, what part of the water do you think either the hydrogen or the oxygen is going to produce an acid?
Hydrogen.
Yeah, the hydrogen part. So when you have the graphite rods in the solution and you see a red color from the universal indicator, that's where the hydrogen is. Now it should be 2 parts per 1 because water is H2O, right?
Yep.
Alright, so keep that in mind, look for that. So we're examining that separating water that is into hydrogen and oxygen requires a lot more energy than just boiling water. And what are you doing when you're boiling water? You're changing the state. Yeah, you're going from like water as a liquid to water as a gas. And we're going to be looking at water again with Boyle's law apparatus. So this apparatus here is going to allow us to measure changes in pressure. Now in the lab, this is filled with water. And you're only going to be able to go to the 80 mark. So on this paper, it says like 800D, that's 800 millimeters. So on your tool right here, where it says 80, that would be 80 centimeters, or 800 millimeters. Everybody see the 80 there? So when you put this into the container, it doesn't go above 80. Does everybody see that? Yep. Sometimes when people put data sheets together, they just kind of get carried away and put the 900 there. Well, the 900 is not possible. You can't get to the 900. So we want to make that clear to you right now, so when you get in the lab, Mr. Stark, if I can get to 900, you can't do it. Now the 300, does everybody see the 300 on here?
Yep.
The 300 comes from the inner tube volume. So I filled this up, inner tube, with water, then I poured it into a graduated cylinder, and it told me it was 300 milliliters. So the volume of the air inside the cylinder is 300 milliliters. That's where the 300 comes from. And that's always going to be V1, so that's the volume of the air. So when you push this into the water, water is going to go into this tube, changing the volume of the air. Does everybody see that? Yeah. So we're examining that change in volume of the air. So where you see H, they have a diagram here. Everybody see H there? H is the amount of water that goes up into the inner tube. So when you're measuring H on this, it's the amount of water that's going up into the tube. So when we get over there, I'll do the first one for you, so you can kind of see how it's going. 10. Now, if you want to count every little dash, yeah. Well, the easy way would be 10. Now, I don't like how they didn't mark D as far as a unit there. It just says D. You just have to go along with how they set it up. Yeah, so at the top, you can just put millimeters if you'd like. But I'm going to recognize it as centimeters. Everybody see that? Now, you're going to want to lift the tube out of the water before you measure it, because you want to make sure it doesn't, because water can seep up in there if there's a leak. So I take it down to my 10, and I'm measuring how much water is going into this bottom tube. Does everybody see there's 1 going in there? It's really about, I'm going to say 11. So H is the water that goes into the tube, and that's going to be 11. Now that's going to be 11 mm. Does everybody see that? All right, so V2 now is the volume of the inner container. So that's going to be, if it's 11 there, then you're going to have to calculate the change at 10, and 1.1 centimeters is the amount of water that goes into the tube here. Now on our conversion factor, 1 centimeter is equal to 3 milliliters. So I need to convert that, so I'm going to take 1.1 centimeter times 1 centimeter is 3. So it ends up being 3.3 milliliters. So 3.3 milliliters of water has been pushed into this tube. Okay? Now, V2 is going to be 300 minus 3.3. So I'll take 300 minus 3.3. What does that equal? 296.7. So that's going to be your V2, 296.7. Now where are we going to find P1? From wave 3. So we have to go to wave 3 and find what the pressure is.
11.5 or
Mr. Steinecker, where do you find these worksheets? Like,
Which one? This one? Be careful, don't crack your screen. Yeah, this came from Ward Science, and that one came from Sergeant Welch. So that is, a lot of students outside of this school are doing this. Yeah, I didn't make these up. This came from like a proven company.
You just said. Can you repeat
This
that?
came from Ward Science. That came from Sergeant Welch. Now we had to improve that because they didn't tell us what the inner tube volume is. If you notice, this is all that they sent. And the procedure is kind of vague. The procedure basically is fill the large cylinder 3/4 full using a barometer, using a barometer to determine the current atmospheric pressure, which we did from wave 3.
How do you find out?
And that's it.
The answers. Do you figure them out? Or
You're
do
going to
they
do
give you an
trial
answer?
1. Well, this one they didn't.
This one they didn't.
No.
This one they didn't.
No, neither one. You just have to figure it out on your own. So you're going to take 3.4 times your conversion factor because the inner tube is 300, and we determined it was really technically 3.3 because this tube is 91.5
So you do
centimeters, but 3 is
3.4.
close enough.
So you do 3.4 times 3.
You're going to do, yeah, 3.4 times 3, and then minus 300, and that'll give you the answer.
Alright.
Then you solve them for P2 here. You're going to take those 3 values, and you'll solve for P2. That is these 3 values here.
I don't think you did that right.
Use the formula on the sheet.
How do you get B2 equals P1? I know, but we don't have
Yeah.
B2 either.
Okay. Now you're going to put your alligator clips.
We didn't know you were supposed to time it.
Okay, you're going to do it more than once. Okay, you've got your clips there. Now you're going to place those into the water solution.
There's really no, oh, B1's right there.
And you should see a color
B1's supposed to be, so
on
it's gonna be the same answer.
one of them. Okay, yeah, you are. You see that? Right here. Which one is, see the red there? Which one is the hydrogen? Yeah, the red there. So the red is where the hydrogen is forming. Because it's changing the pH to acid. This is the hydroxide. So it's really kind of neat when you look at it. You can see that. See the red forming there? So let's there, grab that one. It's kind of like chemistry art. Yeah.
doesn't matter how much we fill this up.
Chem art. See if they fight each other to make water. No.
I did 200 minus, like,
Alright, so this requires electricity to do. And the goal is to use solar power to generate hydrogen gas. Because then you can make electricity for like trains, magnetic trains that travel on like mag trains, yeah, like you see at Disney World. Now, you need some goggles on there, Claire.
Goggles give me headaches.
Well, safety first.
Wait, I have my own. They're right there.
So you should see.
Oh, now they're both
Amazing.
doing stuff.
Yeah, this one, what color is that?
Blue.
Blue. That would be an acid or a base.
Base.
Yes, and this is the acid from hydrogen. So you can see that there is a difference there. So that electricity will. See the bubbles there? That's gas. It's really good. That's the percent of seeing bubbles. Because pH
This looks like it's about to
is a
like
scale
blow
that
up.
measures acid or base, and the hydroxide is what it's determining there.
Can I put the whole thing in?
OH. The reaction is producing that color there.
Do it. Can I put the whole thing in?
No.
Oh.
Wait, so Mr. Snyder, can we just put it in the tube?
Yeah, you're going to put it in there to where you got your first measurement is at 10, right? And the water that goes up in there is the water that's changing the pressure inside the tube. See that? So it goes to around, around 1 or something like that.
There's no numbers on this?
No, you're measuring the data comes from the inner tube. This.
Okay. So 10 is 1.
So 1 represents 10 millimeters.
Okay.
But the conversion factor is in
So
centimeters.
we're looking at like that thing that's moving?
Right.
Okay.
So when you measure that, this conversion factor here will tell you how many milliliters of water is going in the tube. Then you want to subtract that from the air, and that's going to tell you the pressure or the volume of air that's in here.
Alright, so since I'm at 2, I look at this number up here?
No, this one tells you right here where to go.
Oh.
So the 20 tells you where to then take your measurement. And then you go to your 30, you take your next measurement. So you're taking 8 measurements.
So since I'm at 2, I go to 3?
So you're going to go to 20, and then you take your measurement on the water that's going in the tube.
Oh, alright.
And then you go to 30, you take the measurement of the water going into the tube. So the water right here? Yeah. And then you go to 40 and so forth. Centimeter or 10 millimeters. We're going to just say centimeters here because our conversion factor is in centimeters. So 1 centimeter times our conversion factor, 1 centimeter is 3 milliliters, is equal to 3 milliliters. Did it cross out? And then the inner tube is 300, so we're going to take 300 milliliters minus 3 milliliters, and that equals 297 milliliters. That goes here. So what's happened, this water has gone up into the tube, changing the volume of the inner tube. It's decreased the volume. You see how this water inside the tube is decreasing the volume in the tube. So this inner volume is actually air. So the volume of the air has decreased. Make sense? Now we went on the internet and we put to wave3.com and we found the pressure is 29.97. That's inches. And that's the same number all the way down. P1 will be. You can't do 900. So then once you have V2, V1, and P1, you can solve for P2. Just put the data in there and solve for P2.
And
What do you need? Brendan, yeah, put those down. Yeah, you see how there's a deficiency in this tube, but you can still use it. You just
Do we take out water, Mr.
huh? Yeah, you can start it again if you're.
No, it's it was check.
Did you go to 800?
Yeah, we need to go to 80.
Yeah, you should be able to go to 800. You might have to take out a little bit of water because see how it's wanting to spill out a little bit on you. You pour out a little bit of sink.
People are gonna pay to see this when I'm famous.
Oh, you're famous. You can be like, what's her name?
Beyonce.
No, that went to Cameron.
Who? Jennifer Lawrence.
Jennifer Lawrence, yeah, and she didn't graduate from high school. She didn't even get her GED. 40 drops.
40.
Yeah. 40
Oh,
drops.
she's at 4.
40 drops.
Hey, wait, no, don't do that. We need that. Wow. Can I eat it? It's red.
So which one is the acid?
Hydrogen. This one.
Right, so the acid's here.
This one.
And the hydroxide's over here. Ran electricity through it, you would get hydrogen and oxygen, but we've added a couple things to it, like this sodium sulfate. Right. So when we run electricity through it, it's going to favor forming a base in the form of, let's say, like hydroxide. So the hydrogen ions, when you run electricity through there, are going to react with
How is it reacting? Oh.
Well, you're going to see the red there. So this is the base being produced, and this is the acid over here being produced.
That is awesome. Hey, James.
So the hydrogens are going to react with the sulfate, and you're most likely getting like hydrogen.
So that means there's electricity running through it?
Yep. Like H2, SO4, sulfuric acid is probably most likely forming here because of the sodium sulfate. And then over here, the OHs are going to be left over forming the hydroxides.
And what happens if they touch?
Well, you're going to kill the battery.
Ah. That's actually really dope.
It is.
Now the sodium in the water is going to react with the OH and produce the sodium hydroxide. That's what you're seeing there with the blue.
Okay.
So you're making the hydroxides here, and it's reacting with the sodium to give you this solution of like purple there. If you put sodium hydroxide in water, you're going to get this purple color because it's basic.
So what is the time of the electrolysis?
Is that a cellular device?
No, it's not.
How long you allowed it to produce. So the sodium is actually going to promote the hydroxide ion staying in solution. That's kind of what's going on here.
So what's the color? Which one's the electrode one? The black one or red one?
Yeah, the red one most likely is the one. That's the one that's reacting with the sulfate to produce H2SO4.
So electrode 2 would be the purple.
Yeah. Nine. That's when you're going to multiply times your conversion factor. This is centimeters. And you get 2.7. And then you're going to take 300 minus 2.7. And that's going to go for your V2. Okay?